Раз, два, три. Меня слышно? Окей. Welcome, everyone. Today, the topics of our lecture would be transport phenomena. And by this word, I mean diffusion, viscosity, and heat conduction. Heat conduction. Let's start with a very simple example. Let's consider the average speed of nitrogen molecules at 0 degrees Celsius. It's about 400 meters per second. Does it mean that if I open some kind of a flask which contains nitrogen in it, you would feel it or you would inhale it from 15 meters away at a distance 15 meters away after the time S over Vn2 has passed? So that means that if I open the flask, would you feel it after less than a second? The answer is no. Actually, this question was one of the difficult questions why people previously didn't believe in a molecular theory of gas. The average speed of molecules was so fast that some phenomena could not be understood with it. So, in practice, after you open some kind of a flask containing a smelly substance, you would feel it not immediately after the flask has been opened, but after some time. And this time is quite large. It's much larger than a few seconds. The reason why you can't immediately feel molecules after the flask has been opened is that there are collisions. Previously, we have almost everywhere neglected collisions in ideal gas, because we have said that in ideal gas, molecules do not influence their motion. So we can assume that there are no collisions in the ideal gas. But in practice, each molecule has a finite size, and when two molecules are brought too close together, they should have a collision, and the result of this collision is that the speed of the molecule, or the velocity of the molecule, changes abruptly. And due to these collisions, a molecule cannot travel a distance from where it has been spotted at t equals 0 to some other point, let's say 15 meters away, without collisions. Due to collisions, the motion of the molecule, of a given molecule, is like this. And the time it requires to get to a faraway point increases dramatically. The first person to propose a model to describe collisions of molecules of gas was Clausius. And he proposed a so-called model of solid balls. So you can assume that each molecule is a solid ball which has a certain radius r. And due to this finite size, collisions happen. The main result of Clausius, he was able to determine a so-called mean free path. Mean free path of molecules, which is by definition a distance, actually an average distance, traveled by a molecule between the collisions, between the consequent or subsequent collisions. The idea how to find a mean free path is as follows. Okay, let's first consider a collisions between two molecules. If two of these molecules have the same radius r, then the collision happens when the center of the second molecule is found at a distance below 2r from the center of the first molecule. Now, let's for simplicity assume that all of the molecules except for our considered molecule are at rest. So let's assume that all of the molecules remain at the same point of space, while our considered molecule moves at a velocity whose absolute value is equal to the average thermal speed. Then, as this molecule continues its motion, let's say that this molecule has traveled a distance L, we can draw a cylinder which has radius r and the height equal to L. And if no other center of molecule is inside this cylinder, then no collisions have happened. But if there is one, then collision had happened. So if a molecule is inside this cylinder, then at this point actually collision happens and molecule moves further in the other direction, not in the previous direction. And on average, to achieve one molecule in this cylinder, on average, we need for L to be equal the following value. So we need L multiplied by pi multiplied by 2r squared multiplied by n, where n is the number density of molecules, gives you an average number of molecules in such a cylinder. And on average, we have one molecule when this product equals to 1. This is actually the product of number density and the volume of the cylinder. So typically, from this, we obtain the following expression, where we have introduced a new value, which is called collision cross-section. Sigma equals to PD squared is a collision cross-section. And we get this result. Maxwell made this formula more precise. So he considered a more complicated case when all the molecules move at random speeds according to Maxwell's distribution, and he included motion of other molecules. He didn't assume that other molecules are at rest. And he was able to obtain a more precise formula for a mean free path. And he got n by sigma by square root of 2, where this additional factor of square root of 2 is due to a relative motion of molecules. Due to a relative motion of molecules, their relative speeds are greater than average thermal speed. And due to relative motion of molecules, collisions happen more often than if all other molecules are kept at rest. So this can be considered a precise formula for a mean free path. Now let's consider a so-called distribution for free propagation lengths of molecules. Let's assume that we have a number of molecules moving at same speed through the gas. And inside here, collisions may happen. So let's assume that the number of molecules in this beam of molecules is n0 before they enter this gas. And we are interested in the distance which these molecules have traveled before the first collision. So let's assume that each molecule traveled a distance of Li, and of course these Li are random values because there is almost no way for us to predict what distance would be traveled by each of these molecules. So this is a random value, and thus we can introduce a distribution for these values. Distribution which is described by probability density. So this is probability density. So in order to determine this probability density, so we want to find this function. It is yet unknown. In order to determine this probability density, we consider a probability for these molecules to have a collision in the small distance dx here. And this small distance dx, if we assume that the cross-section of this beam equals to A, cross-section of this beam equals to A, then in a small volume corresponding to this cross-sectional area and this small distance dx, we find dn, which is A multiplied by n multiplied by dx other molecules in this layer of gas. Then after we multiply this by a collisional cross-section sigma, we get the probability for each molecule to have a collision in this small distance element. So for the probability, we divide everything by cross-section area A. So this is sigma n dx. Now we have an equation for the probability for the molecules to be found at a distance x from the entrance into this gas layer. And the equation is as follows. dp over dx equals to minus sigma n dx. So that means that if I count the number of molecules at a distance x from the entrance and have found that this number of molecules is some part of the initial number of molecules n0, but this number n of x over n0 is the probability that the molecules haven't experienced a collision in this layer. But if I move further and determine the same number some distance away at x plus dx, and thus calculate p of x plus dx, the probability for the molecules not to have a collision over a distance x plus dx, then the second number would be lower than the first number due to the fact that a certain number of molecules have experienced collision in this small layer dx. And this is the change of p. That's why I can write this equation as dp over dx is minus sigma n dx. And this equation can be easily solved. I use the variable separation method. Okay, no dx here. Minus sigma n dx. And okay, this should be also multiplied by p, because the number of molecules having a collision should be proportional to the number of molecules which have already been here without collisions. So that means that n of x plus dx is equal to n of x minus n of x multiplied by this probability dp, sigma n dx. That's why after I divide everything by the number of molecules n0, I get this equation. And this equation can be solved by means of a variable separation method. So I get p to this side and obtain that d natural log of p equals to minus sigma n dx. And by integrating this equation from x equal to 0 to a certain number x, I get that natural log of p is equal to exponent to the power minus sigma n x. So in the end, the probability for a molecule to not experience a collision over a distance x, okay, equals to this exponent. So the number of molecules which didn't experience any collision decreases exponentially as we go from the entrance to this gas layer. And this equation actually has a name. This equation is called Beer-Lambert law. And this equation has many different applications, including nuclear physics. Because if you want to calculate number of radiative isotopes which has been stopped from escaping the reactor, you can use also this equation. But at the beginning, I considered a different problem. I want to find the probability density for a molecule to have a collision at a distance from L to L plus dL. So I want to find the probability density. Okay. So what I want to find is probability density to have collision after traveling path L. Now, since I determine probability density, that means I need to count a number of collisions which have happened when the molecule has traveled a path in between L and L plus dL. And how do I calculate this probability, this number of molecules? I just subtract the number of molecules which didn't have collision after they have traveled this path from the number of molecules which didn't have collision after they had traveled this path. So what I get is rho of L dL, the probability to have a collision in this interval, is equal to P of L minus P of L plus dL. So this number is e to the minus sigma n L minus exponent e minus sigma n L plus dL. Or I can write it as in a derivative form. This is actually equal to minus dP over dL multiplied by P of L. Minus dP over dL multiplied, well, not by P of L, but multiplied by dL. So this derivative is actually equal sigma n multiplied by E minus sigma NL. So the probability density for the molecules to travel past L without a collision is given by this formula. From this formula we can determine mean free path again. Mean free path can be calculated as the following integral. Let's denote mean free path by a letter lambda. Lambda is given by integration from 0 to infinity of the free path L multiplied by the probability density for a molecule to move this free path, sigma n E minus sigma n L and dl. Actually, this integral can be easily calculated by integrating by parts, and the final result is 1 over sigma n. Okay, so that's it for the motion of molecules inside the gas. And let's continue and determine how often these molecules collide. So let's answer the question, how often collisions of molecules happen? First of all, let's consider a single molecule and answer this question for this particular molecule. We already know that molecule moves at an average speed of V average, and it experiences a single collision after it moves after it travels a distance of L. On average, it experiences one collision after it travels distance L. That means that average time between collisions is, well, L over mean speed, over mean thermal speed of molecules. And if I answer the number about the frequency of collisions. So I want to find the number of collisions per unit of time, and this is mean speed over mean free path. But what if I consider collisions which happen in a certain volume? Then we have a large number of molecules in it. We have large number of molecules, and this number of molecules is given by multiplying number density of molecules by the volume, by the considered volume. And then we calculate number of collisions R by summing up collisions of each individual molecule. So I multiply Nm by a frequency of collisions, mean speed over L. But I need to divide this number by 2. And the reason why should I do this is that I count all the collisions twice, because in all of these collisions, 2 molecules participate. So if I calculate the number by summing up collisions of each molecule, I count all collisions twice. First, I count a collision when I sum up collisions of the first molecule, and the second time I add the same collision is when I count collisions for the second molecule. So that's why when I divide the total number by 2, I will get the number of collision events. So this is N multiplied by V multiplied by mean speed over 2L. And then I remember the formula for L, for the mean free path, and I get after which I get the average number of collisions per unit of time in a certain volume. Okay, so now we slightly understand that a huge number of collisions happen inside any kind of a volume which contains gas. And due to these collisions, a number of phenomena happen. First of all, let's consider a diffusion. Diffusion can be of two types. One is when we consider molecules of two different types. So we have two different gases, and we have a mixture of these two gases. And we have a vessel which contains these two types of molecules, and for some reason, we may have created a situation when the number density of molecules of type 1 in this part of the vessel is higher than the same number density for these molecules in the other part of the vessel. At the same time, the ideal gas laws require us that total density of molecules, so as P equals to nkt, and for the mixture of gases we have N1 plus N2 by kT. That means that if we have this gas in a state of mechanical equilibrium, then N1 plus N2 should be constant. As I have said previously, if we have different types of deviations from equilibrium, then mechanical equilibrium is established fastest. So the time to establish mechanical equilibrium is least of all possible times. So that means that first of all we can assume that total number density of molecules is constant throughout all of our vessel. And then due to the difference in the number density of the molecules of the first type in different parts of the cylinder, the second part of the equilibrium establishment process will happen. And this second part is the diffusion of molecules from the regions of higher number density to the regions with lower number density. And this diffusion process can be described by Fick's law. Fick's law of diffusion. And this law states that if we place anywhere, or if we select mentally somewhere any kind of a surface, then the number of molecules passing through this surface, per unit of time, per unit of surface area, should be proportional to the derivative of number density over dx, where x is an axis which is directed orthogonally to the selected surface. Okay, let's add a direction to this formula, since let's assume that n increases with x, so that means that here the density of molecules is higher than here, and that means that flux of molecules goes from that side to this side. And that means that the flux of molecules is directed in the direction which is opposite to the x-axis. That's why often in the Fick's law we add minus here to respect this fact that molecules move from the region with higher number density to the region with lower number density. Now let's calculate this coefficient of proportionality, which is often called diffusion coefficient. Diffusion coefficient. Okay, so this is D12. Well, there is another situation which is called self-diffusion. I have not told about it previously. I have said that we have two types of diffusion. Diffusion when we have different types of molecules, and we can also have a self-diffusion. Self-diffusion. This is a diffusion which happens when we have only one type of molecule. But as we have said previously, if we have one type of molecule and this one type of molecule is in a state of mechanical equilibrium, then the number density of these molecules is constant. That's why the concept of self-diffusion requires a few additional words about what we mean about self-diffusion, because there is no derivative of this number density over any direction. So if I choose any direction, the number density will be constant, and that means no macroscopic motion would be observable here. But let's say that we somehow place a mark on a part of these molecules. And then observe these marked molecules. So let's assume that in the vessel we have marked molecules somewhere here, and all other molecules are unmarked. And then we observe how marked molecules will propagate. And due to this diffusion, these marked molecules would go to different parts of this vessel. Would go to different parts of this vessel, and eventually the number density of marked molecules should become constant. But before that, the number density of marked molecules is not constant, as we have marked molecules only in a certain region of space. So that means that we have indeed these derivatives of number density for these marked molecules. And again, this Fick's law of diffusion implies that the number of marked molecules passing any selected area here, crossing any selected plane here, is proportional to some coefficient which is called the coefficient of self-diffusion, and multiplied by the same derivative of n over the direction which is orthogonal to this selected plane. Okay, let's write it. I'll write it as g equals to minus d multiplied by dn over dx, where by g I mean the current of molecules. The current, okay, I can say current density of marked molecules, which is actually the number of molecules passing per unit of area per unit of time. Now let's proceed and connect these coefficients to the molecular quantities which describe the motion of molecules in the gas, like mean free path, average thermal speed, and whatever else. So for simplicity, I would derive the coefficient of diffusion only for the self-diffusion. So I'll derive coefficient of self-diffusion. Self-diffusion. Then this is the selected area. And I watch how molecules cross this selected area. So we have molecules above the selected area and below the selected area, and we have events when molecules cross the selected area from bottom to the top, and when they cross it from the top to the bottom. So we have process in different directions. And what we know is that we know the mean free path of molecules. So we can assume that the molecule which is located at a distance which is lower than L can cross this selected area without any collisions before this crossing. We are interested only in the molecules which can cross it without any collisions, because we can predict motion of each molecule only within one collision. So if we know the number of molecules in this layer and their speeds, then we can count the number of molecules crossing this area. So the number of molecules of interest is approximately equal to the number density at x, which is equal to, let's say that this coordinate is equal to x0, and then this is x0 minus L, multiplied by L, multiplied by an area, yeah? So this is the number of molecules, and for this number of molecules, it takes time equal to, per unit of time, only this fraction of molecules can cross the selected area. But this is not everything, so this is not a complete formula. I know that the direction, not all of these molecules will be able to cross the selected area. As we know, molecules move in different directions, and those of molecules which move from this selected area will not be able to cross this area. For simplicity, let's assume that we have six major directions. Upwards, downwards, left, right, and forward and backward. Only those molecules which move in the upwards direction would be able to cross this area. That's why I need to multiply this by 1/6. It's a simplification, because instead of considering the continuum of directions, the direction which can be characterized by any point of the sphere, we restricted our considerations to only 6 directions. This is also for the sake of the simplicity of the derivation. So I now have this formula. Number of molecules multiplied by the number of molecules crossing the surface per unit of time. Okay, now I can do the same for the layer which is located at a distance L from the selected area, but above the selected area. So for the number of molecules moving in the downward direction, crossing the selected area in the downward direction, I get this similar formula. So altogether, the current of molecules is as follows. Now I substitute for these values in this formula and get and now I have this difference where L, I consider that L, mean free path, is a very small distance. And I even assume that when we move at this distance, then the number density changes only slightly. That's why I can use Taylor series to represent these number densities and write the following, that n at x0 minus L is equal to n of x0 multiplied by dn over dx multiplied by L, and then I subtract n of x0 minus dn over dx multiplied by L. Finally, I get for the current of molecules 1/3 multiplied by mean speed multiplied by L, where L is the mean free path, multiplied by dn over dx. And also I add minus sign here because I have for both of these terms I have minus sign before them. That means that the current, if we increase the number density when we go from the bottom to the upward direction, that means that the current will be directed in the opposite direction. So from this formula, comparing it with the fixed law of diffusion, I obtain a self-diffusion coefficient, which is equal to 1/3 multiplied by mean speed multiplied by mean free path. And actually, I would like to say that despite that we have used a very simplistic derivation procedure, which involved a huge number of simplifications, it turns out that this formula is actually correct. It turns out that this coefficient is a precise coefficient which we would have obtained if we considered all the complicated stuff, if we have considered that all of the molecules move different distance before the collision, and if we have considered that the number of directions is infinite, is actually that all of the directions can be presented by a corresponding point on a sphere. But we will get the same result. But this derivation procedure is much simpler. So that's why I stick to this procedure, because it allows to include much of a complexity, but at the same time to explain how this diffusion process happens. Okay, now let's have a small break for 5 minutes. Okay, let's continue. So previously we have discussed self-diffusion and have determined the self-diffusion coefficient. And I would like to say that not only molecules can transfer through this area, but these molecules can carry a momentum, and also then they carry energy. And for this reason, other two transport phenomena arise. One of them is heat conduction. When we consider heat conduction, we assume that number density of molecules everywhere is constant. But at the same time, the temperatures in this vessel are different. So let's assume that below we have a somewhat lower temperature, and above this area we have a somewhat higher temperature. So there is a temperature change with this distance. And now let's calculate the energy which is transferred by the molecules which move from the above to the bottom. and moves from the bottom part to the upper part, to the top part of this vessel. Okay, using the very same concepts as we have developed for the diffusion, the amount of energy transferred per unit of time, per unit area, okay, per unit of time, through the area A is given by the following equation. We have 1 over 6 multiplied by number density of molecules multiplied by A multiplied by mean speed. And these molecules, they carry higher energy with them. So let's assume that these molecules carry the energy as CV over CV multiplied by the mass of each molecule. So CV is the heat capacity at a constant volume per unit of mass. So this is a specific heat at constant volume. And if I multiply this CV by the mass of each molecule, I obtain the heat capacity of a single molecule, and then I multiply it by the temperature. And here we have a temperature of multiplied by temperature T, but at the bottom part. So this temperature is calculated at the bottom part, X0 minus L. And for the molecules which move in the downward direction, the energy which is transferred by these molecules is given by this equation. It's again a very simplified version of formula, because here we don't consider the differences in average speed, and also here we don't consider difference in number densities at each of these layers, which might arise because we know that pressure is N multiplied by K multiplied by T. So when we have a higher temperature, then we have somewhat lower number density. And we don't consider all of this, but we just consider the simplified energy flows. And then we get that for the heat transfer rate through the unit area of the surface per unit of time, so dq over dt divided by A, which is the area of the selected surface, I get, this should be E upwards minus E downwards divided by the selected area A, and then I get 1 over 6 multiplied by N multiplied by M multiplied by thermal speed CV, by thermal speed V multiplied by CV, and now the temperature difference T of X0 minus L minus T of X0 plus L. And then for calculation of this temperature difference, I use the same trick as I have used for the calculation for the number density difference. So in the end I get 1 over 3 multiplied by, this is actually number density multiplied by mass of each molecule. This is equal to the density of the gas, density multiplied by average speed, multiplied by CV, and multiplied by L, and here dt over dx, and also minus sign, which should not be forgotten. So this is the formula for the flow of heat, and often when we describe heat conduction, the following statement is often used for description of heat conduction. Fourier law of heat conduction states that the amount of heat per unit of time per unit area is proportional to a so-called thermal conductivity coefficient multiplied by the derivative of temperature. Multiplied by the derivative of temperature. So that means that the heat conductivity coefficient here, kappa, is given as 1/3 multiplied by rho multiplied by V average multiplied by CV multiplied by L, where L is the mean free path. Okay, similar can be applied to another process which is called viscosity. Similar approach. Viscosity. Here we also consider some selected area, but there is a macroscopic motion of gas along this selected area. So and we assume that the velocity of this macroscopic motion increases as we increase the coordinate. So we assume that V of x plus L is greater than V of x minus L. But actually it doesn't matter. We can just assume that they are different. But for simplicity, to achieve understanding what kind of process happens in these conditions, let's assume that the velocity here is higher than the velocity below the selected area. So now consider the following. Each of the molecule participates at the same time, it participates in two different motions. One of these motions is a directed motion, and this is a motion as a whole. So we have some kind of a drift of these molecules. And another type of motion is a random thermal motion of molecules. Due to the presence of thermal motion, molecules cross this selected area, which separates part of the gas which flows at slower speed from the part of the gas which flows at higher speed. And each of these molecules carries some momentum. An average momentum, which is carried by the molecules from the bottom part of this vessel, the molecule which carried from the bottom part, is equal to m, where m is mass of the molecule, multiplied by v of x minus L. While the average momentum carried by the molecules located above the selected area is similarly calculated as follows. The average momentum of thermal motion is 0. So when we calculate average momentum, we only include this drift motion or ordered motion of molecules or motion of the gas as a whole in this expression. If there is no drift motion or motion of layers of gas in a hydrodynamic sense, then no average momentum would be carried from the bottom to the top and in the other direction. Now we calculate again the average momentum carried from the bottom part to the top part per unit of time, per unit area. We use the same approach as there, and we get 1/6 multiplied by n is a number density, multiplied by, okay, area is excluded because we have divided by this area, multiplied by mean speed v, thermal speed, and we should multiply it by the average momentum. So I add m v of x minus L minus v of x plus L. And I get minus 1/3 multiplied by density multiplied by thermal speed, okay, multiplied by L and dv over dx. So the average momentum carried by the molecules is being transferred from the upper part to the bottom part. And that means that after this momentum is being transferred, the velocity of the bottom part in the bottom part of the gas would increase, while the velocity in the upper part of the vessel would decrease. And as a result of such process, this process would facilitate establishing the equilibrium between bottom part of the gas and the top part of the gas. Because due to this moment transfer process, at the end, the process will continue until these two speeds will become equal to each other. So as a result of this process, this difference in speed would be decreased. So this is a force which facilitates the decrease in the difference in speeds. And this process is actually known by a process of viscosity. And the main law of viscosity is as follows: that tau, the shear tension in the fluid would be equal to viscosity coefficient multiplied by dv over dx multiplied by this minus sign. So that means that this coefficient presents a viscosity coefficient in the ideal gas. This is the third transport coefficient. Okay, now let's continue a bit further. So we have previously considered the influence of thermal motion and collisions on the process of energy transfer, momentum transfer, and particle transfer in gas. And now let's introduce an equation which describes temperature difference or density evolution in the gas. So let's consider a following diffusion equation. So we can write the following diffusion equation. dN over dt at some certain point of space should be equal, in one-dimensional case, it would be equal to d over dx of diffusion coefficient multiplied by dN over dx. So let's try to understand what this equation means. In this equation, we assume that number density is only a function of x coordinate. And this equation aims to to answer the question how the number density would change as a function of coordinate and time. So let's assume that at certain point of time we have some distribution n of x of number densities over x coordinate. So at some point here, due to the difference of number densities in the surroundings, there would be molecular flows which would aim to change the number density at this point. So let's consider a small region which has the thickness of dx, and the number of molecules in this region is given by n of x multiplied by dx. Now the inflow of molecules, okay, actually I would write this in other direction. So I assume that number density increases as a function of x. So the inflow of molecules is calculated as g of x plus dx over 2. So since this thickness is equal to dx, and if the center point has coordinate x, then the coordinate of the right bound of our region is x plus dx over 2. So the inflow, according to the Fick's law, is given as d, diffusion coefficient, multiplied by a partial derivative of n over x at x plus dx over 2. And here we can also assume that diffusion coefficient is also coordinate dependent. Diffusion coefficient might depend on the number density or might not. We are not interested in that. We just know that we need to calculate this expression at x plus dx over 2. This is inflow of molecules. And the outflow of molecules from the selected region is given as g of x minus dx over 2. The same expression, but calculated at x minus dx over 2. This is outflow. And then to calculate the difference, g of x plus dx over 2 minus g of x minus dx over 2. So this difference between the inflow and outflow would change the number density in this region. So dn over dt multiplied by dx equals to g of x plus dx over 2 minus g of x minus dx over 2. So we consider here g as a function of x, and we calculate it at two close points. And then we use this trick again, as we have used previously for many times when considered diffusion, heat conduction, and viscosity, and we get that this is equal to dj over dx at the point x multiplied by dx, which is the difference between arguments x plus dx over 2 minus x minus dx over 2 gives you dx. And then I calculate derivative multiplied by the change of by the difference in arguments. After I subtract dx from here, I get this equation: dn over dt is d over dx of j of x, where j is this flow according to the Fick's law of diffusion. And now I can insert in this expression d multiplied by dn over dx according to Fick's law. And this is how I get a diffusion equation. In a similar manner, I can obtain a heat equation. But except for the molecule transfer, I would consider heat transfer. I would write this equation without similar derivation, and okay, I would write the following: rho multiplied by CV multiplied by d temperature over dt, so partial derivative of temperature over time, would be given by d over dx multiplied by kappa, which is thermal conductivity coefficient, multiplied by partial derivative of temperature over x. Okay, and this would give us heat equation in the following form, in one dimension. The heat equation. So here is the thermal energy which is contained in the small area which has the thickness of dx divided by this area width dx. And here is the difference between the inflow of heat and outflow of heat from this region. So this difference is the disbalance between heat inflow and outflow, and this disbalance causes the temperature in this region to change. And finally, the last remark about these equations is the following: that according to these equations, let's say we initially have this kind of a distribution of, let's say, temperature as a function of x. So constant temperature everywhere, and there is an elevation of temperature in a small region. And if we try to solve this equation, after some time, even small amount of time, the temperature distribution would be given by the following function. And the tails of this function are exponential, so they have this type of a dependence, minus so these type of tails we have here. And that actually means that if we look at this distribution for a very small amount of time, delta t, we would have a temperature rise which is not equal to 0, even if we consider the coordinate change which is above the product of speed of light multiplied by delta t. So according to the heat equation, heat propagates at an infinite speed, which contradicts the well-known rules from relativistic physics, that there is no process which can happen at a speed which is above the speed of light. The reason for this is that we use a few simplifications. When we write this equation, we don't consider underlying processes of molecule motion. We average these processes and we assume that the time between the collisions is very small compared to the characteristic changes in time here. That's why we get this continuous type of equation, differential equation. But we don't consider any kind of a discrete process like collisions and motions of separate molecules. At the same time, according to already known distributions like Maxwell distribution for speeds, this factor has finite value even if the speed of molecule is greater than the speed of light. But of course, it's impossible to observe any kind of molecule which moves at a speed which is somewhat even close to the speed of light, because the probability of such event is so small that it can be neglected. So we have a probability distribution here which has some finite value of the probability, but when this probability is something of the order of 10 to the minus 10 to 100, then there is no sense in discussing any kind of molecules which can possibly move at such speed. Here we have some kind of a similar condition. All of the heat transfer process is carried by the molecules which move at finite speeds, and everything like this, so this discretization is neglected when we write this equation. At the same time, we are somewhat precise when we deal with this heat equation, because these tails at the region when x minus x0 is greater than C delta T are often presented by the heat rise which is of this kind of order. So this is unpractical heat rise and it can be neglected. So the reason why in the heat equation we assume that heat propagates at an infinite speed is due to the model restrictions which we use when we write this heat equation. Thank you for your attention and see you next time.